Okay. So,
Okay, we have
oh,
also the
okay,
Shale.
that should
Yeah,
not make
just
it.
okay. So we're just giving a couple of minutes for people to join. Um, okay, let me just start sharing my screen. It's already 8 with 1 minute, so I guess we can start. And I'm guessing the rest of the people will join in the next minutes. I muted you for a minute just to kind of to start, but please unmute yourself if you want to say something or give an opinion. Please don't hesitate. So thanks for making it today. Like I said, today we have a short meeting. Uh, given the difficulty to find some presenters on the specific topic that it was suggested for today. Um, so the agenda that we have for today is just a quick administrative update, and then we move to the main dish, which is talking about elite by elite breeding. Um, as I said, it was difficult to find. I mean, we have many examples in the CG, but it's been difficult to find some volunteers to tell us about what they are doing. I know several breeders that do excellent elite by elite breeding, but we just couldn't get them on time. So, but at least we'll have the demonstration on the quantitative genetics concept, where Chris Gaynor from the Roslin Institute have made some has some important points to share on the elite by elite breeding and how they can make a difference in the programs. Of course, as always, these presentations are just always like a starting point for a discussion among the COP members. So please feel free to give your opinion. Um, don't keep it only for you. And then we'll just have that discussion, and then we're going to close the meeting. So just to don't entertain too much the people, I want to remind again what is the purpose of the COP. So, you know, maybe I will actually change the name of the meeting because I keep it like breeding scheme optimization, and some people has been confusing if that is related to their programs or if this is just the COP. I will change the name to the invite to at the very beginning be called COP. But you know, the purpose is to really create a safe forum to discuss many topics related to breeding scheme optimization and general blossom management, and also be a place where people can share um, tools, methods, services with our partners, the private industry, or EIB, etc. So just some additional things that I would like to mention is that there is some new manuals in the toolbox. There is one that a consultant, Ian McKay, uh, recently finished, which is, from my perspective, really good. It talks about the different surrogates of genetic value, from the phenotype to using means, to using blues, blobs, etc., the differences, and how to calculate them, just in case you want to take a look. I think it's a very well done manual. There's also some new vignettes on genetic gain in the toolbox. Before we just share the scripts, we converted those scripts into vignettes, and so you can actually see an explanation associated with the code, and also see it as an HTML in case you don't want to recreate the code and you just want to see what were the results from those scripts. Um, so in the next meeting, also to share, I'm talking with Juan to see what would be a good topic, but we also want to wait for the feedback on the rest of the people. What would be a good topic for the next meeting, and but BSU has volunteered to present something. Thanks, Juan, for that. Um, and if you want to volunteer to present something that you're doing, please don't hesitate. Just send me an email. You can tell me, oh, look, I'm doing this in Cassava, which I think is really good and modern, etc. We'll be happy to share it and accommodate it with the specific topic that we want to deal on that meeting. Okay, so before we jump into the main dish or the topic from Chris, Does anyone has a question, comment, something that you want to share on any of these topics? Okay, good. You can tell us later when we finish maybe discussing the main topic of today. Chris, are you ready to take from here? I saw that you
Yes,
were around. Okay. And as I mentioned, this is just to trigger a discussion, but Chris, please, I don't take more of your time.
sure. So trying to kind of really show the value of doing kind of an elite by elite crossing and comparing it between, say, using more of an exotic source of germplasms, pretty tricky, which I think is why it's hard to find a lot of people to come in and talk about it. Mainly because the trade-off really depends on what you assume that that exotic germplasm is like. So I'm going to kind of make the argument why you might want to really heavily use these elites more by making the argument of how you want really early selection of parents and how that improves the breeding program. And basically I could support that if you have, say, a closed program and you're picking early, that both theory, some practical experience and simulations, they all support that really picking parents early is the best choice. And of course, just how early you go requires a little nuance in terms of how accurate you're measuring traits. And I'm going to kind of gloss over some of this nuance for the moment and just focus more on the main message of wanting to pick early. And my tie-in with this with elite parents is the assumption that you're best going to accomplish picking early by using elite parents because you're recycling within your own breeding program. Hence, you're kind of shortening the generation interval as much as possible. Whereas opposed if I were to say pick more exotic sources of germplasm, it is often usually an older line. It had maybe been developed by another breeding program a while back, or even if it never finished the end of their breeding program, it's been in their system for a while before it then comes into your own program and gets evaluated. And to kind of highlight this value of kind of going early, I'm going to give just a simple example here using a simulation, just based on kind of a double haploid wheat program. So I'll talk through that example simulation really quickly. I'm assuming in this little simulation, I'm just going to do one breeding cycle. Say we start with, say, 50 parents, make 200 crosses. Each cross will derive double haploid lines to get us up to about 100 per cross to get us up to 20,000. And then we're going to go through a series of yield testing. First, just kind of visual selection to get down to a preliminary yield trial, and then actual formal yield testing for multiple stages until here by year 7, we just have a variety that we release, which we say is just the best line that we get, that we observe. So to kind of show what that looks like, if we look here at just the kind of the mean value of the individuals in each stage, this is done over 100 replicates. So the variability here shows each replicates. So this initial kind of head row stage, the parents, I assume their mean of 0. The crosses were made at random. So of course the head row, there's been no selection. So the mean of that is 0. We see then this kind of jump here representing kind of what we get from visual selection, so I assume visual selection is fairly inaccurate, but we do have a fairly strong selection intensity. So we do get a decent bump, but the big bumps really come when we go into the yield testing phase, when we go from the first and then to additional yield testing phases. We actually, until we reach our variety, which we get a fairly high mean. And of course, this kind of highlights that the multiple stage testing scheme works as we expect, where we're improving yield over time. By the end of the stage, we have something that's fairly high yielding. We also have fairly good confidence in it, and that's what we release in variety. Now, to kind of highlight the value of maybe going earlier, is let's look at what happens if I were to try and select this variety earlier. So here I have in red is what I just showed you before, which is just the average of the trial. And then in blue here is what if I was to pick what I think is the best line based off the current available data. So I'll start here at this elite yield trial, and then the individual I think is the best line here is the one I release as the variety, so hence these distributions are the same. And I think if I went back one stage earlier and say my advanced yield trial, and based off that data I tried to pick a variety, you'll see I get pretty close to the mean here. So based off my assumptions here that I'm getting nearly to what the best variety is, slightly less, a little bit more variability in here. So it is showing that I'm getting maybe a little improvement for the release of a variety, in the sense that I'm on average doing a little bit better by doing this extra stage, and I'm being a little more consistent. And in practice, I probably couldn't really release variety directly from the stage anyways, because I still have to go through a period of seed increase to release variety. So you're still gonna, even if I could get a really good guess of what could be a variety at this stage, I'm still gonna probably do the additional testing. However, if you were thinking about it as picking as a parent, well, you could pick a parent and you have plenty of seed to cross at this stage. So it shows that really by crossing at this point from these best lines that I'm getting nearly the same thing I would if I had gone back through the additional stage of testing. But what's even more interesting is if I go back another stage and we see again, there's a lot more variability out of this first yield trial, but still a reasonably high mean. So I'm not losing too much. And of course, this is just picking the one best. And when I'm actually making crosses, I'm not just picking one parent, but I'm picking multiple parents. So if you looked at kind of what you can get from getting the best individual within multiple guesses, you'll find that you do a pretty good job capturing that best value. And more importantly is I'm shaving time off by picking this earlier. And I'm really making these early selections. So if you think about response to selection and realize that it's all kind of divided by generation interval, you realize that we're getting more gain. And I can show that here really quickly just by scaling by generation interval and just dividing by it. And now when you look at this, you can see at this stage here at PYT, I really get the maximum mean. So even though I might not be picking the absolute best line, by picking it sooner, I'm actually doing better performance and better gain. It suggests that really you want to pick parents soon and recycle them, and you can take kind of multiple guesses at this. So I guess if I were to summarize this simple simulation, I'd really say that kind of these lengthy testing schemes that we are typically used in breeding programs are really good for producing varieties because they help ensure that your variety tends to have a high mean, you're less variable, so you're more confident in what you release. So it's kind of a nice conservative approach that usually matches up with, say, a farmer's need for a variety. However, for parents, you don't need to be so conservative because you're able to take lots of chances by making lots of crosses. So you really want a shorter testing scheme with kind of the short generation interval. And that's when I think I showed there with the by scaling by generation interval. Okay, so that was all pretty simple simulation. And I kind of want to talk through a bit more nuanced simulation that we ran here with cassava that kind of highlights a few other issues a few other items that simulation didn't show. And it shows that things get pretty complicated. So in this simulation, what we did is we had a kind of a fixed breeding program, and we were looking at how many parents do you choose. So we were looking at, say, 4, 8, up to 64 parents. And then we're also looking at kind of where you pick those parents from. So you can pick them from the PYT, which is this red line, or you can pick them from the AYT, which is the green, or you could do kind of a 50-50 split here of both PYT and AYT. And you'll notice when you did the split in this breeding program, it showed a massive improvement relative to picking all from one generation or the other. Part of that is because you're able to kind of interlink generations within the breeding program. And also because the simulation had kind of genotype by year interaction variance. And by accounting for this, we're kind of really giving us more robust selection of individuals. And the other aspect I'd like to show here with kind of how many parents you pick is notice where these maximums are here. So this is after 20 years of the breeding program. And you'll see a maximum here just around 16 parents. So a very small number of parents was able to do really well. And then even if we went further out to, say, 60 years, you still see the maximum still here around 16. We can see more in the AYT and PYT how this starts here a little smaller and shifts a little bit to a higher value as we move forward. So obviously how many parents you pick kind of depends on how long-term you want the breeding program to run. But this result kind of is, we've seen in other simulations as well, that not only do you really want to pick kind of these elite parents, pick them early, but you also want to do a fairly small number of parents so that you can really recycle quickly. And I guess with that, with all my quick assumptions and real basic things, I'm sure there's lots of questions, a lot of discussion to follow on that. So fire away.
Yeah, thanks, Chris. That was a good presentation. Before we actually start the discussion, I would like to see if there's questions on the content, because indeed, I think you went relatively fast. And maybe by the time that they were picking up, you were already moving. So is there questions about the content? Gary? I can see that
Yeah,
you have your hand raised.
do we just, when we're looking at the value estimated from different levels of testing, did you assume, what assumptions did you make about testing resources from, stage 1, 2, and 3? If in a typical plant breeding program, where we don't differentiate between selecting varieties and selecting parents, there's a lot more, normally a lot more replication after the PYT, or the stage 1 trial. And in my own work on this, I've found that unless you shift resources into that first stage, as you're recommending, you don't get necessarily an improvement from the reduction in the cycle time. So what assumptions did you make about that allocation of testing resources?
So in the previous one, I just assumed it was a single location, and I believe the heritability on that was, I think it was 0.5. I have to go back and remember what it is. So it's a reasonably accurate selection in that stage. So,
For the PYT.
yeah, for the PYT. So,
Mhm.
and then I
And for
assumed
later stages?
at later stages, you had more locations, you hence had
Mhm.
much higher heritability and much more accurate. So,
There may be a high heritability for a single location PYT.
yeah. Yeah, I think I ran it with and without genotype by year interaction variants. I think the ones I showed there didn't show it. The other simulation I had that with it, it actually showed very much the same result. And with the genotype by year interaction variants, you would have decreased the heritability quite a bit. And we've actually seen that in quite a few of our simulations, that our
Mhm.
results seem surprisingly robust to some of the assumptions we make. So we can kind of move the heritability around, and we still tend to see the same trends. For example, in the simulations where I was showing kind of, if you want to pick parents at, say, the PYT or AYT, depending on the assumptions I make, I see it maybe bounce around a little bit between favoring the AYT or favoring the PYT, but I pretty much never see it really favoring, say, the third stage of testing.
No, no, you don't see that. But there, in my experience, there is if you use variance components that are typical of the programs that we work with, there is a substantial difference between, very limited testing at stage 1 and more extensive testing at stage 2 versus shifting, a little bit more into stage 1, and then it really shifts the balance.
And I think that's where the trade-off is, right, Gary? I mean, sometimes PYT seems to be better because of speed, but it's really losing the accuracy. The AYT is almost as good, even though it's much slower, or yeah, it's slower in general. The accuracy is good, so it also helps. But I think it's when you combine those two that it seems that you
Yeah.
make that big jump, because that you're really taking the best of both worlds. Um, there is a question on the chat that I would like to read. Is from Peter. Uh, it says, just for you to check, Chris, if you select from the PYT and the AYT, do you wait to advance until you have both data sets and do the G by E analysis, or you can put the PYT parents directly into the crossing block? I think that's what you're suggesting, or the simulation is suggesting, right, Chris? I mean, you first put the PYTs immediately as soon as you have the simple data set for that, for the PYTs before the AYTs.
Yeah, so in this particular simulation, yeah, I assumed as soon as you have analyzed, say, your PYT data set, you pick the best from that and then send them straight to the crossing block. So the time frame I'm usually assuming is in summer you harvest, you get your yield data, and then in fall you're starting your crossing. So, uh,
Yep.
yeah, so in this case, my PYT parents are ones that have been evaluated in the PYT and then are being used for crossing based off that evaluation, and the AYT parents, the ones that have been evaluated in AYT and are being used based off that data.
What is really, really interesting for me, Chris, and I would like to get the feedback from the COP, is that in most of the programs that we've been simulating the optimal size of the programs, checking how many parents is optimal, 10, 20, 30, 100, etc., as you mentioned, it depends for how long you want to breed. I mean, if it's for, let's say, 20 years, 30, 40, 50, 60, the number of parents will increase. But what has been surprising is actually that looking at even the assumptions from the programs where they share their variance components, their generic correlations, multiple traits. The truth is that it seems that actually the more complex the product profile is, because you have more traits, it doesn't mean that you actually need to keep more and more and more and more and more parents. It seems that actually it takes more time to actually accumulate those those good alleles from the multiple traits in a population. So it seems that it's always favoring a small number of parents, which is actually quite nice, and goes good with some of the literature that was also published in Mace in the 80s. That you really need a small number of parents to make progress for a long time period. In this case, is even still 60 years, and the parent maximum or the optimal seems to still be 16. And I think is not well understood that if you actually put more and more and more and more and more parents, it's not that you're just keeping diversity, you're also affecting the genetic gain. You can also already see that from moving to 16 to 64 is making a relatively strong impact there, for a good percentage, probably like that 10%. So I don't know, what's your impression on that, Chris, and maybe also for the COP, any comments there?
Sure. So I guess I'll mention what the parents chose in this simulation. It's under the assumption that we're picking kind of a small number of parents, making crosses at random, and kind of keeping all those populations and moving them forward. That's not always representative of all breeding programs. One is certainly there's often some sort of thought into how you make combinations of crosses. Also, you don't necessarily keep all the populations moving forward. An alternative strategy, which I think you can get similar results, would be to use a slightly larger number of parents, make more crosses, and then eliminate crosses before you get to the actual yield testing and before you really spend lots of money on the individuals. And I know more commercial maize breeding programs do this, where they'll make quite a bit of crosses. And maybe the first couple of generations that are relatively inexpensive, they'll keep the material around. And then before you really start reaching the point where you have to invest quite a bit into these crosses, you'll decide to keep or discard them. Now, of course, if you do that, what you have is effectively kind of like what we're simulating here, that really there's probably only a small number of parents that ultimately ended up contributing.
Yep.
So I realize it's kind of an alternative way that initially uses a lot of parents, but probably finally uses kind of a smaller number moving forward.
Yep. Yeah. I think that's been the general recommendation to the programs once we do the simulations. I mean, they can have in the total program much more parents, but it seems like at least for a specific pipeline or product profile, they don't need to have that many. There is additional questions. Just first to close the one on cassava. So Peter, this indeed, I'm assuming that Chris is using the results from the simulations that he presented last time to the team. So the assumptions are basically what the cassava actually does. So no off-season nursery, so PYTs and AYT ratios based on what the breeding team has presented. Because Joseph is also asking about what is the proportion of lines, well, in this case, individuals selected from PYT and AYT, because in cassava, they are not lines. But yeah, Joseph, if I don't remember the exact number, but we are using what the breeding program is presenting. So what they do, that's what we are doing. But in general, I think when we look at the ratio of PYT and AYT, so Chris, I don't know if I'm going in the wrong direction, but it depends, right? We're always talking about the trade-off of accuracy versus speed. So when you try to bring more individuals from the PYT, it's like putting more weight on speed. And when you bring more individuals from the AYT, it's like putting more weight on the accuracy. And depending how bad is your accuracy, of course, you may want to actually put more parents from AYT, but if it's not that bad, as Gary was mentioning, actually, if you have good levels of resources in the PYT, you actually want to put more weight into the PYT. Does that help, Joseph?
Yeah, thanks. That's okay. Thanks.
Yep. And before I move to the question from Wolfgang, there was one before from Harish. Chris, are you assuming the PYT are done at representative TPEs? Is it important because we have early generation testing of sufficient number of recombinants and families, 2 at multiple locations, 3, and those locations represent the TPE? Chris, do you want to say something? I mean, this is definitely an important topic when we talk about recycling elite by elite.
Yeah, so there's essentially a couple of key assumptions here. So one is obviously that the environments I'm evaluating are representative of my TPE, and also that what I've evaluated of traits is really representative of kind of my target value. So hence I'm kind of capturing all the important traits. That if, say, example, I'm working for a wheat breeding program where end use quality is really important, I may not have a very good measure of that in, say, PYT, and I may only get that at, say, a later stage when I can start doing some of the quality testing. And those sort of nuances that I kind of mentioned before that I was glossing over might shift you more to this advanced yield trial testing. But also, when you're kind of in this realm, is you can maybe think about how can I maybe get some of these elite quality testing to kind of move it earlier, and how can I rearrange the flow of my breeding program to try and pick those parents sooner. So I guess there's kind of the static, if this is what the pipeline is, you can kind of analyze your data to figure out where's kind of optimal to pick parents. But also based off that, you can maybe think, how can I rearrange it so that I can pick parents early more confidently? And I think that's kind of the focus that most breeding programs should be, is figure out how can I get all the information that's really important at the earliest stage so I can reasonably pick parents.
Mhm.
And then you can think about the later stages as more building confidence for release of variety.
And you can see actually more or less in the plot that indeed he's showing that the PYTs are kind of representative of the TPE, because if they were not, the truth is that the accuracy would be lower and lower and lower. So at some point, the AYTs would be better just because they go to more locations. Of course, the speed always has an impact on why PYT could be better, but that's where it gets hurted. So Wolfgang, you have a question.
Yeah, it's a relative simple question so that I get an overview. And this, if this is a continuous simulation or discrete simulation, what I mean, is it a simulation of single selection at events, or is it numerically?
I don't think I captured completely. I don't know if Chris, you got it. Can you say that again, the last part, Wolfgang?
Yeah, it is so in simulation you can do model calculations which are based on numerical calculations. And the other part of simulations are that you are simulating uh, uh, selection events and populations with individuals and select within these. So is this numerically or is it with a discrete simulation?
So I guess, I think if I get the definition right, I think it'd be more than discrete, where I'm using AlphaSumR to kind of simulate genomes and then assign QTLs to loci, assign facts, and actually simulate the individuals. And I did two different things here. In the first one, it was just a simple create parents, create progeny, and look kind of what happens through just one kind of cohort material. This more complex one here is actually more of a continuous process where it's actually more representing a real breeding program in operation. So it's picking parents and it's actually recycling and making new by simulating meiosis. So.
Also, I think, also, okay. One thing what I want to comment, because you have here this in this slide, these 4, 8, 16, 32, and 64 parents. Also, this is, I mean, the response to selection has also an error. And what is very interesting, that with doubling the number of parents, you'd reduce the error of the response to selection in discrete simulation studies by 50%. Although this is because of this, how it is shown here, 4, 8, 16, 32. I thought it was a discrete simulation. But it is, also it is interesting with that with the number of parents that we can operate with much less parents as we think.
Yeah, that's a good comment, Wolfgang. And just remember that even though Chris is simulating phenotypes, etc., at the end of the day, what he plots in results in the gain is the actual genetics, not the phenotype. But just to as an additional comment, Gary, you also have a comment or question.
Yeah, I'd like to get back to that accuracy issue at the
Yep.
PYT or AYT stage. This is actually a very important point. So remember that if you're getting an accuracy of 0.5, a heritability of 0.5 at your initial selection stage, that's an accuracy of 0.7. That's a very high accuracy.
Yep.
Now, looking at the variance components that come out of most of our trials and the level of replication, very often PYT even for CG programs is a single location. We're not getting anywhere near those accuracy levels. So two points about increasing accuracy. One is if we select out of any stage, as you've pointed out, from narrow populations, 8 to 16 parents, on the basis of a GEBV, we'll be increasing our accuracy, increasing our heritability, and getting better predictions of the breeding value of parents out of that first stage. The other issue is that we need to redesign our breeding networks, our testing systems, so that we do get 3, 5, even 6 or 7 stage 1 trials, not necessarily replicated. Standard practice in most commercial breeding programs, large commercial breeding programs, is to run between 5 and 10 stage 1 trials or PYTs, according to this terminology, that are not replicated. So we need to put those networks in place. We can't run them ourselves. It means we have to structure our breeding networks so that we are doing our stage 1 testing with our national system partners. But we need to try to get up to that accuracy level of 0.7 or heritability level of 0.5 at stage 1. And we need to know what our accuracy and heritability levels are. At the moment, I think there are a lot of programs that can't express or estimate what their heritability levels are at their stage 1 or PYT level.
Yeah, I'd say I'd agree with those comments. So yes, certainly this 0.5 that I did before was pretty accurate. I think I did it before with the G by E, and it would have been down to about 0.25. Again, the message was similar, but there's obviously less of an advantage of doing a PYT relative to AYT. And really, I wouldn't give a blanket comment, say, I'll pick for AYT, pick PYT. I would agree with what you said, that you really need to be able to evaluate the data in your own program and really determine what your accuracy is. And more importantly, is determine what your accuracy is for estimating kind of your true breeding goals, so not just in individual traits, but kind of the whole goal itself. And then that would kind of help you really decide when you can start picking parents.
Yeah, thanks, Gary. And yeah, just to add on that, I think is, as you mentioned, it's interesting that just the levels for accuracy at the single site are not being reached. Let's say 0.5 heritability. But even if you have a very high heritability in that single location that they are testing, you highlighted an important point, which is that they also need to try to go with their partners to cover more locations, because even if they have a super high heritability in that location, if that year that was not representative of the TPE, then there's not too much
I mean,
value.
that's right. The heritability from a single location analysis is meaningless. It's simply the ratio of the plot error to the combined genotype and genotype by environment effects, most of which are not going to be repeated. So it's if you can't make these decisions based on
One location.
heritability estimate from one location, unless it also includes separately estimated genotype by year, genotype by location, and genotype by year by location components.
Yeah, it could be that you're lucky and that location is actually very representative of the average TPE. But if you're not, then you're making a very efficient selection, but not for the region that you would like to. There was a comment from
In my
Joseph.
experience, you're never lucky.
Yeah, that's a good one. Joseph, I thought you had a comment. I don't know if it took so long for me to call you that. That you
No,
didn't
no,
know?
it's okay. I don't know whether so if I look this graph, the cassava simulation, so the gain relative to the mean, if I say the AYT, there is no gain. Is that my reading, or because in all cases, whether the 4, 6, 8, if you select only based on AYT, there is no genetic gain?
No, yeah, I think that's a good question. And I think that this is just related to how Chris scaled. I mean, Chris, can you just tell us why you had to scale to understand better?
Yeah, it relates to the way it was scaled. So all within a set, you took all scenarios and scaled them to kind of a standard normal, so that mean was 0. So that's what, I guess, relative to say the average amount of gain across all scenarios.
Okay, that
so
doesn't mean that you're having negative gain, right? It's just that it's taking the
positive gain. Just if you were to consider all possible scenarios, it would say that, say, this one here is worse than average than the others, which you can kind of clearly see in the plot. So
it's just like if you were normally scaling, Joseph. So because you scale it with the mean 0, that's why you have some negative values, but it's not going in the direction that that you were saying.
Okay.
That's a good question.
To make the plots look nice, because if I don't do this, then the error from the difference in gain from, say, one replication of the simulation to the next becomes pretty sizable, and you kind of don't see the differences until you kind of take out the replication effect, which is basically what this scaling is doing.
So the next question, thanks, Joseph. The next question is from Kevin, and he's asking, are these 16 parents a situation of NE equals 16? So in practice, this might be more lines than 16, or what exactly do we mean here?
So this would be 16 actual parents in the simulation. So the NE will actually be smaller because it's a closed program that had been operating for quite a while. So I'm not keeping track of the specific NE in the simulation, so I don't know what the final value is, but it'll definitely be smaller than the 16 because you would have selected a lot of very related individuals.
So it's actually 16 lines being used as parents that they might come actually from a relatively or healthy effective population size. Let's say that the program started bringing the best 30 lines, and then, but as the program really moves, what it's telling you is that as the program evolves, you want to have a small number of parents that optimizes for a given time period. So what we are doing with the programs is to also ask them, okay, for how long would you like to actually keep this program running? And of course, we always assume short to medium time periods, and it's still favoring the use of very small number of lines. But yeah, as Chris mentioned, this is actually actual 16 lines, but the effective population size might be a bit smaller because it's a closed system. Jan,
could I jump in for a second?
Yeah, please, Kevin.
Yeah, I just noticed, frankly, that this is cassava, and that's a whole different ballpark, because I assume that these parents are extremely heterozygous clones, and so the diversity issue goes out the window. But if we're talking about maize or wheat or, I don't know, I guess any other non-clonal crop, I mean, there would be differences in terms of what would be the numbers of parents needed. This is, it's a hugely important question in CIMMYT. We're talking about this, what should be our effective population size, how to calculate the effective population size from the number of crossing parents. But still, I find this quite interesting. Thank you for the
great catch, Kevin. This is customized for cassava. I mean, that's why we are doing this exercise with the different crops. We did something similar for sorghum, something similar is going on for sweet potato, etc., etc. And indeed, it depends on also the complexity of the genome, and the complexity of the product profile, I mean, how many traits, etc. But in general, even for programs like sorghum, we're not finding the optimals to be much higher. It's maybe a little bit higher, but not as much as you would expect. It's not like you have to double it. it would be like maybe the optimum is in 25, something like that. I think that was the recommendation actually to sorghum, like using between 20 and 25 after doing something similar. But yeah, I think this needs to be customized for the crop. That's why we get information about the genome complexity. I mean, number of chromosomes, length, initial effective population size, because that would also affect the results. I mean, if you start with an effective population size in the simulation that it was 2, of course, that will not, even if you develop a lot of individuals, in year 60, it will not have the same results that when you started the breeding program. So we normally take what is the current effective population size and then simulate some years in the future. Great catch, Kevin. Jan, do you have a comment or question?
Yeah, a comment. I think putting some of these principles that we talked about here into practice, or trying to apply them to real breeding, and building on to what Gary was saying, having one testing location at the early stages is akin to playing roulette, because about 10% of the time, your data might not be representative of the true TPE, and so your selection is basically random. It is not really targeted to the TPE, and also I think it is important to have more locations so that you have a higher chance, a higher probability to harvest material that is truly representative of what you're after, the traits you're evaluating, and then also be willing to discard locations if they don't look good. If you learn that at the early stages, there were some events, either Mother Nature or some mechanical issues that make some of these testing locations unreliable, that you discard them and not further invest in going through with harvest. And so that's some of the practical applications of utilizing some of the things, the principles that we learn here, to really apply them into a real breeding program. It's absolutely key that where you're testing represents TPE, and that you get good data out of this. Otherwise, again, it's like playing roulette.
Mm-hmm. Yeah, great comments. Dorcas, I think you also have a comment.
Yeah, I think a comment was sent by accident privately to me. It's from H. Badwaj, and it's that it's proven beyond doubt that elite by elite strategy works, and works very well. However, majority of the CG programs still do not believe in it and do not practice that. How can we as leaders encourage our breeders to adopt this strategy?
Yeah, that's a great question. Chris, do you want to say something? Maybe just something from my side very quick. I think that's what we're trying to do with these exercises, and try to simulate exactly what they are doing to show them that there is value and not too much risk in reducing the number of parents, that actually by reducing it, they can achieve greater gains, and they can still keep running the program for many, many years. There might be others and other opinions. So I don't know, Chris, do you want to mention something, or also someone else from the COP want to say something about it?
Sure, I'll mention, so before I started doing all the simulations, and I worked as kind of an assistant breeder and been in breeding programs, and I think a lot of the assumptions I would have had probably represent a lot of other breeders. And part of it is we were always concerned about diversity in our breeding program. Oh, we're getting too narrow. And it wasn't really until I delved into some of these simulations I realized that some of the concern about diversity is probably not as reasonable as we think it is. For example, I would have thought before I had gotten into this that the optimum number of parents would have been much larger, and I would have expected, say, 64, and I would have never thought down to 16 would have made sense, until now that I delve into more of this and realize, oh, actually these small parent numbers work, which again shows that you can actually, by keeping yourself fairly narrow and really turning over quickly, you still maintain a reasonable amount of diversity and keep making advance. And if for more empirical experiments, you can look at some of like the long-term selection programs they've had in maize, where the effective population size is very tiny, yet they still make gain over 100 plus years.
Exactly.
So I guess there's both the simulation results and the empirical evidence kind of points to this. It's just not, I think, what most people realize, and because we kind of have our kind of assumptions beforehand that we don't think that's the case.
And Gary, your comment goes in this direction, or should I move into the other questions before yours?
Yeah, it's related to population size. It's not just simulation that gives us evidence that small elite population sizes are optimal. There's an immense body of practical literature from maize breeding in the Corn Belt, from academic studies that supports this. Another important element of using closed elite populations is that's where genomic selection works. It doesn't work in large populations where relatedness is low. In the context that we're likely to be using it in. So if we want to use genomic prediction, we have to make sure that our populations are closed. Just to follow up on Hans's point, that there are ideas around among breeders in the system that are simply not correct, that we are diversity limited in most of our programs. This is a huge problem, and it's affecting the rate of genetic gain that we deliver to farmers all over the world. We are, in a lot of cases, by not adequately helping our breeders move along in their understanding of quantitative genetics and selection theory, we're actually, reducing the progress that we deliver. We can't leave this to the interest and inclinations of breeders to make all of these decisions on their own without support. So I think it's really good to have these discussions. The community of practice is really important, but we need to put in place a formal training system to make sure that everybody's working from the same level. If you're a CG breeder, you need to have a world-class support system behind you, a world-class understanding of how to design a pipeline. So we need to think about how we're going to actually not only work one by one with the pipelines, but implement some form of formal training to get everybody up to a common level. I wonder if you've sort of been thinking about that in the EIB.
Yeah, that suggestion has been given in the past, and we are pretty much supporting that. It's just that we're at the point that we are developing the knowledge. I think we are getting to the point where we feel more comfortable. I mean, this is just one aspect, is the size of the program, but also we have something on selection strategies, or whether hybrid breeding versus or line breeding. I mean, how much is the difference? How many testers is the optimal? I mean, there's many questions, and I think we're getting to the point where we have enough knowledge to convert all this information from the different CG programs that we have learned into a training that I think can achieve that mission that you're mentioning, Gary, which is bringing everyone to the same level, understanding the concepts. So yeah, I'm completely up to it. I'm expecting that really by Q1 2021, we might be running the first one of these trainings. Currently, we're compiling the knowledge, like I said. We received this suggestion in the past, so it's not like we just forgot about it. We are considering it. But yeah, great suggestion, Gary. Thanks for those comments. Yeah. I'm just going to address very quick some other comments in the chat. So first one, Peter was saying, if we use 16 parents, can any of these from the trait introgression, can any of these parents be from the trait introgression pipeline? How many parents can be devoted to introducing new germplasm without destroying the pattern? or in this case, the allele frequencies? That's something, a very interesting question that we received last time, and we are I mean, we are busy, but we are also designing some of the simulations to also understand how big is going to be the impact of trait introgression, because we always say, okay, we understand that we need it to keep not only the pipeline running for 60 years, I mean, to avoid that the diversity gets depleted. We still don't have the answer. So great question, Peter. I expect that we will have that answer coming soon. And just for Johannes to the question that he asked is the same that Joseph asked about the y-axis. Is just the scaling the results to have mean 0. It doesn't mean that you have negative gain. It's just scaling to have a nicer plot, because the simulations come from different scenarios. And then Kelly is asking, do you put any controls on how narrow the parental crosses are? Do you place limits on inbreeding in the 16 or select only on EBB or GEBB? I don't think you're making any sort of optimal contribution in these simulations, right, Chris? I mean, we've been assuming that we just select for.
No, in this particular simulation, it was just random crosses. There's no maintenance of diversity in the parents. There is some inbreeding depression being modeled, and because of that, and because it's phenotypic selection, it'll inherently force you to kind of pick more heterogeneous individuals to advance. So you do get a little maintenance of diversity in the sense that if you don't maintain diversity, you'll see inbreeding depression, and it'll reduce the mean. So.
Yeah, because this could actually have a big impact as well. We've been simulating some of the programs. What is the effect on applying something similar to optimal contribution, really considering the inbreeding, etc. And that can have an impact even in making this smaller number, even the optimal for longer term. So it's not like, so if you were doing optimal contribution, actually, if I understood properly, Chris, I would expect that even the number of parents would be a bit smaller, just because you would be handling so well the genetic diversity. So these numbers are actually very encouraging, even with some of the assumptions. And because we don't have too much time, I guess that just quick question, quick answer to Johannes and his question. Is surprising the small size, 16 for 60 years. I would have thought, like Chris, more like 32. Yeah, I mean, we're also kind of surprised. We always thought that probably 20 to 30 was the optimal for this time period. It's actually turning to be smaller, which is interesting. But at the end of the day, I mean, we are considering very complex profiles, so multiple traits, adding G by E, which includes genotype by location, genotype by year. And even with the different genome complexities, there is some differences, of course, but they never go that far. They are always depending on the time period, and they are always in some of the lower bounds. Of course, if you put 150 years, of course, then you will start to bring the optimal, let's say, to 32 or 64. But I don't think that's the goal of these CG programs, to think, well, maybe they should, but it's better to think on a short to medium time period and come up with the right strategy for introgressing diversity to make sure that the diversity is not lost. Jan, you had a comment.
Yeah, I just want to comment and build on what Gary and also Hans brought up. So as EIB, as an organization, we understand, the fear, I guess, among the breeders, the CG breeders, to miss out on genetic diversity. Yeah. So we've sat down with Eduardo and Sarah and Mike Olson, and really we want to come up with this clear strategy. So Eduardo is really focusing on the elite by elite, and these simulations and models that are being built is focused on that, and to address some of these concerns of, okay, what do we do when we want to add genetic variability? We want to do that in a very structured way. So Sarah and Mike Olson will take on that space and come up with a very well defined strategy plan on, what do you do, what things do you put in place to make sure that when you do an introduction of non-elite germplasm, how do you go about it, and when do you introgress some of, for example, new traits into your breeding program, so that that can be addressed in a very disciplined way, and not just on the side having programs that might dilute the advantage that one would make within an elite by elite program, if this is not done in a very structured way.
Thanks, Jan. I'm gonna.
Eduardo, this is Tanda. Just
Oh
a
yeah,
comment.
Tanda, please go ahead.
Yeah. So an important point regarding diversity also, I think, there's a lot of worries about, we are going to lose genetic diversity, but I can also argue that we have too much genetic diversity that can get in the way of actually identifying good products. So in trying to think about that question, I think we have to go to the other way and ask, when is diversity too much?
Yep.
And what balance should we strike in terms of diversity? I mean, you can look at, I don't think we have to do it like temperate breeding program, commercial ones, but you look at the germplasm base that currently makes the current germplasm pool is not that big. It's very limited. On one side, it's probably 3 or less than 5 lines. Do we need even 16 or more? And when is diversity too much to actually get in the way of identifying good lines and products? I think we have to think about the other side too.
No, that's a great comment.
Eduardo, Sankalp, I just have a small comment.
Yeah, please, Sankalp, go ahead.
Hi. So I think this is a classical discussion I think we have heard as well. There's a lot of evidence in the literature. Industries also support that with a very small number of individuals, which are designated as elite and proven over years of testing with genetic merit. I think it's important for us to also understand what they really mean by diversity. Is there a defined scheme of crossing in the second model alternative? If there is none, at least we have a closed system and a schema that follows it, and also a recycling strategy. So if that doesn't exist in the previous argument, I think we'll have to also make we have to say that clearly what diversity means, and can they quantify what they mean by diversity there in some cases, right? So just a comment, but it's important to be mindful of that. I think I just wanted to bring that.
Thanks for sharing that, Sankalp, and thanks, Tanda. I think those were good comments, and I think everyone now is thinking about this this topic, and so I hope that this was useful for everyone. There is some difficult parts to accept, especially because that are very interested in the diversity. I don't want to finish with the controversial comment, but Gary put something like, we don't need to worry about gains for 60 years. 20 is plenty. If we exhaust the variability after 20 years and anyone wants to pay for more breeding, then we can create new populations. I mean, you always have their gene banks, and as Sankalp is saying, as long as you can keep diversity and you have a good introgression strategy and a good closed system, the fears shouldn't be there. And I guess that because we have to move with to another meeting with the ICRISAT team, to talk about hybrid breeding, so I have to close this meeting. But I thank to everyone for staying the entire hour. I said that it was going to be short, but actually took the entire hour. So I'm happy to see that people was interested to comment and express their ideas, whether they were to support or to also make us think. So I appreciate it. Thanks to everyone. Thanks to everyone that participated, and we'll talk soon, whether privately or in the COP. Have a great day.
Thank you. Thank you, Eduardo. Thank you.
See you in a minute.
Bye-bye.
Bye.
Bye.
Bye-bye. And thanks, Chris, for presenting.
It's 15 hours.
Yeah, it's 15. Bye-bye.